go ahead.
Awesome.
Okay. Hey guys, my name is Ankit. Uh, I work as an RL researcher. I have my own startup. I'll talk about that later. But yeah, presenting this paper, which is basically an idea where you can use something like a soft verifier instead of using hard verification. In bio, this becomes an important problem because the hard verification is you going to a lab and essentially running the kind of experiment before and then get the reward and back propagate that to a model. So instead of that, you already have a lot of real world data in bio. They trained a sort of a surrogate model, which calculates the probability of how two genes are going to interact with each other and which goes up and which goes down. And essentially use that surrogate reward as a reward signal for the model to backpropagate. They use more techniques around it and they find some encouraging results, but that's the crux of the model. So yeah. To start with, they do not have access to exact rules facilitating the formal verification, right? So testing hypothesis in a lab is the way to do it. Real experiments is expensive and does not scale with computation. So this is where you have approximate oracles with prior knowledge, which utilizes a prediction model instead of going with experimental data, and they use RL in that. That's what I explained before. Uh, and the results here are that soft verification essentially distills the biology world models into an LLM, uh, and can achieve the kind of performance on the leading benchmark compared to the state-of-the-art models. And essentially, they also combine verifiers with chain of thought, like verifying the chain of thought reasoning, providing a reward if the reasoning is correct, and that improves the performance further. So that's the idea. I mean, they initially talk a lot about the problem, where at one point you have a lot of annotated data in the just a sec. Yeah, at one point you have a lot of annotated data in the industry, but there is no way to use that data as such because they just created a sort of co- models around it, but it did not really do anything outside of bio. So they want a way for people to be able to reason with it, to be able to utilize that knowledge, and talk to it. As simple as that. So yeah, there is something known as a virtual cell models that have come up recently. Virtual cell models are, I think it was promoted by Arc Institute as well, Arc Bio as well, where they are essentially creating a virtual model of the cell and model how it would interact with the environment. So, which shows that you don't need experimental data for all of this, and you can generate predictions for any cell state transitions, such as a disease to healthy state and vice versa. And there is a very specific modality for this, such as transcriptomics and imaging and genomics, or even language. But most of it is not trained on multiple modalities, and that's why it's like very specific model for a very specific task. You don't have a generic model that can do multiple things, and that's the goal of this paper. Like here, you have to develop a method which allows for integration of world models into a common space, and they use language as a connecting modality. The benefit is that it allows transformation of complex models into conversations and can engage users. Uh, by distilling a biological model into an LLM, they're able to distill the knowledge derived from experimental data to a natural language that enables interactive and human readable dialogue, which can be seen as an alignment of reasoning LLM to a biology world model. But essentially, it talks about a biology world model and an LLM a lot. So the whole idea is that you have a lot of experiments in bio that you end up in a place where if you can put it in a LLM and then you can just interact with it. But yeah, it keeps talking about it for 3 to 4 pages. And they build upon a lot of aggregation of world models that are already there in a representation space. And then They use models of biology to train models which are just as performant and can bypass the need of large-scale data generation. Uh, they mentioned it at the last in the paper. Their base model is Qwen 2.5. It's struct at 4 billion parameters. So everything that happens at the 4 billion level, 4 billion parameter level. But yeah, the results are very interesting even for at that level. And they even compare the results of the base model with how much they were able to improve the model. And the core capability that they are relying on is the generalization, especially out of domain, as well as at looking at unseen problems to see how it goes through. Generalization also skips through a couple of things. Sometimes they say that if a model has not seen the test data, that is generalization. Sometimes they see that it's a novel problem, that is generalization. So this is the core aspect here. There is a new, they use something like a surrogate model, reward formulation by a domain-specific biological model, where they calculate the probability and give you an idea of, uh, give you an idea about hey, how much this is gonna last. To give you a simpler example, think of it as isomorphic labs generating a protein structure. Uh, for that, a reward cannot be that you just go to a lab and test out that protein structure. You already have a lot of data. And an easier way to predict is just have other model which predicts the stability of the protein structure. If the stability is zero point 0.8, you pretty much have zero point 0.8 as the reward. So they call this soft verification throughout the paper because this is not a hard verification. Hard verification in their language is going to a lab and testing this out. So this is then they arrive at a model which they can talk to, which can reason and do things. Uh, their entire experiment is on a narrow set of perturbation prediction. Uh, what happens when given a couple of gene to other genes if you knock down a gene in a given cell? So yeah, in that sense, it's quite narrow, but I do think that it's gonna generalize. So
And Keith, let me interrupt here. I think just for the sake of people who don't aren't familiar with genetics, either you or I should describe what knockdown means. You want to do that?
you should go ahead with that. I have
Yeah.
a very basic understanding of it.
Yeah, I mean, I don't have a really complicated, but basically it just means you use CRISPR or other techniques. What CRISPR is a way that you can basically remove a gene from a genome and then look at the impact of that. So that's called knockdown, just to be clear. Yeah, so like typically you would look for the change in expression of other genes or other phenotypic responses like, like disease or not disease or something like that. Sorry. Sorry to interrupt.
Not an issue. So basically, I mean, this is pretty much the strategy that they use. They use GRPO throughout. And one surprising thing was they do use GRPO even if they are getting good trajectories. But I mean, that is the GRPO throughout. So the B part where you see training, you have prompts and completions, and they have advantages that they do. This third thing where the source of verification is that there are some hard verifiers that they have used, but the ideas around it are one is experimental data and you backpropagate a hard verification and a reward to an LLM. Then you have a virtual cell model that you use as an input. You get a soft answer, you use a soft verifier based on that, get a reward, and backpropagate it to an LLM. The third part was they created a lot of knowledge sources in biology. So when a reasoning LLM has a reasoning trace, what they ended up doing was essentially create a reward based on the reasoning trace and how much it corresponds to the knowledge sources. They add this as an additional reward to either A or B, and then backpropagated that as well. Or rather, not A, but just B. And this is the claim here is that this is what improves it, improves the model performance a lot compared to the base model, and it kind of performs to a level to the state of the art bio benchmarks.
not to spoil the um to give a spoiler though, but I think that this claim is a little bit off because I think whereas you look at the beginning of the paper and you think they're saying, oh, if we combine experimental data plus virtual cell model plus knowledge sources, then we get better than any of the three. When in fact, the experimental data all shows that experimental data alone outperforms virtual cell model and knowledge sources, even if experimental data or virtual cell model is added to experimental data, right? And I think that that's a really disappointing result for me, and they don't really talk about it. So I just want to,
Yeah.
just to be clear about what the claim versus the reality here.
Yeah, that's true. So that was something that struck me as odd as well. But I do take it as that, say, if you don't have enough resources for an experimental data or the experimental
Yeah,
data experimentation is slow, you can pretty much use a proxy and get to a level which is closer to
that's
what a experimental benchmark would be.
yeah, yeah, no,
So
absolutely. It's not a total loss, but
yeah,
the way that they write the paper makes you think that the former, but it was really the latter.
I mean, yeah. So I guess that's their incentive, right? So anyway, so basically the whole idea becomes that uh, you have something like we are talking about knockdown, right? Is this particular cell line likely to result in a differential expression of gene V? Is what we are predicting here, and that's the task. Usually, earlier it was done through bespoke models that are trained on task-specific data or foundational models pre-trained on large-scale corpora, which was the kind of proxy models that we are talking about, the prediction models. And the recent literature and the recent experiments in this regard show that the bespoke models tend to outperform models under the found that fall under the second category, which is foundational models pre-trained on large-scale corpora. So, but creating bespoke models requires large amount of specialized training data that is either annotated or obtained experimentally in a lab, which is costly, and most of the labs do not have the kind of resources, and most of it is also biased towards one side, which they also talk about later. But yeah, so I mean, the bespoke models already exist in a manner, so they tend to use the previous bespoke models as the reward signal. So yeah, reasoning models trained using software verifiers learn to generalize on out of distribution data set and task, bypassing the need to train on experimental data, which is the final thing. So they also have something known as a foundational model for transcriptomics, which uses the kind of biological knowledge that models have learned during pre-training runs and get it to the task specific questions and basically able to predict better. So essentially, if you take Quen, which is like a general model, and then you're getting to an rbio, which can learn to reason about tasks like perturbation, which was not really a part of its original training data, although we don't know what went into Quen's training data. But there is a very likely chance that the model wasn't trained on specific tasks about reasoning, like reasoning in situations like perturbation. Then, of course, this is probably the summary of the entire paper, where they're able to I mean, I'll just go through it once again, before I come to the method. Essentially, the whole idea is that you're distilling knowledge from a biology world model to a reasoning models that everyone can use instead of being very, very specific and task-based. Essentially, then they find out that our bio can learn to reason about tasks like perturbation, which is I just mentioned, then uh, they also show that virtual cell models can be used to tutor rbio1 with soft verification, and which the kind of knowledge that they learn from here is inherently transferable and generalizable. And of course, multiple source of verification can be composed together and become better. And all of this that they were doing, they were not using test time chain of thought. All they did was just use RL to train further. Think of something like a Sonnet 3.5 and 3.6 before test time came out. and Kimmy's current version.
So I want to, so my opinion here is, so, and I want to hear, Ankit, when we get to this section, this number four here, multiple sources of verification. This is, I haven't seen a paper that uses a technique that they use here to combine, and I think it's really clever insight about GRPO because they use this like sort of group relative, right?
Yeah.
So that relative, so basically you're kind of normalizing to your relative performance so that you can combine signals from multiple verifiers and they're automatically normalized to the same scale. And so I don't know, I feel like that's maybe the algorithmic nugget from this paper, and they really don't do a good job of explaining it.
So, yeah, I mean, the paper is more focused on the bio topics. I was reading it more from the algorithmic side of it. And so I do think that it makes sense that the more reward signal you can provide to a model, the better it's going to perform. Right. I mean, we are essentially debating based on thinking machines blog about how even bits of information in a reward signal works pretty well. So, and on paper, at least in theory, it makes sense. But how you do it and whether the signals are confusing, whether the credit assignment is right or wrong, is what probably ends up making a difference.
Yeah. I mean, we saw with the DeepSeek paper last, whenever we read that recently, uh, and also the previous DeepSeek, that they like tend to use rollouts, right? They train these specialized models for each domain and then roll it out, like take the best rollout from that from like a from like when you like you re-roll out from those specialized models and then just do regular uh um regular pre-training on that. And I thought, or like post-training, I guess. So that like I found this interesting contrast to that where we're saying we're just going to throw all the different reward models together into one giant reward function that you pick like on the fly or something like that. And so that like I yeah, anyway, I thought that's what I really took away from this paper from the algorithmic side.
So, of course, they use GRPO, which is the first method. They have a clipped surrogate objective because of the surrogate part where they have an epsilon. I mean, they clip it in a sense that they don't fully use that. This is a typical GRPO math. You have the clipping as well, and essentially you end up with a reward function, which is just based on the probability of the given substrat, sorry, the cell, the gene, and the verification there. So, this is the whole idea around it. You have a verifier, that's the typical GRPO notation, the probability of Q, O, I, and a V. Then you have a hard verification which directly comes from experiments, which is simply one if the experiment works, one if the prediction was false and the experiment is results in false as well, otherwise zero. That's typically the first method that you're supposed to use here. Then you have something like in the soft verification that comes in using virtual cell models. So essentially, instead of going back to something like a one and one when it was true and true and false, they have a probability of whether it's gonna be working or not. So essentially, it's not an experiment, it's just a prediction. And that's where you have a soft, where verification is not an experiment, but uh, more of a prediction model. So this is what you have, where they just use two genes and then basically pass it through a virtual cell model to predict that whether the perturbation would happen or not. So they also have uh, point-wise mutual information scores around it. They basically create a log of it. There's a lot of math that goes around here. The whole idea is that you have to normalize this and you have to bring it to a level where the reward signal is meaningful and does not outshine the reward signal from the previous hard verification. So That's there, and it comes from the top 0.05 interaction with the highest scores in rbio experiments. Now, the third was the using prior knowledge, which they use knowledge sources and use that to assign a reward. That's another soft reward. That's just analyzing the chain of thought as well as the reasoning, as well as the output that is there, and just assigning a smaller reward based on ontology or whether or not the model is on the right track. It's row-based scores, keywords-based scores, and likelihood estimations. So that's how that those are the different methods that they use. Essentially, their entire uh, reward is you have. I mean, I'm gonna skip through all the maths, but essentially, their entire reward is the summation of all the three methods, and that's the final thing that they backpropagate. Wherever whichever method is applicable, but perhaps if the VCM cannot give you a result, then you don't use that.
So so I was kind of uh baffled why they use Rouge score and that when in like keyword search rather than use LLM as a judge here. Uh, I didn't
Yeah,
under
I think they could have done that, just that they went with one method and they thought that it's working. The other side is that in this case, because the reasoning chains would have a lot of very specific keywords based on the subject matter, so it's an easier score for that.
Hmm.
But for a generic model, probably that won't work. You
Yeah.
need more stronger methods there.
Yeah. I also thought the last one here, the likelihood based verifier, I don't know, I didn't quite understand this. Did you, my interpretation of this was to look at the sort of the log likelihood um of the ground truth or like the output like sorry, the log likelihood of the knowledge source for that model and they use that as a score. Is that like how you interpreted that?
I interpreted it more simply. Of course, they take a log and everything. Uh, but these likelihood based verifiers are based on this thing, where they essentially are estimating it as well. Like I was talking about the Rouge based verifiers and others,
Yeah.
right?
No, no,
Ultimately, yeah.
the log one. The other ones I understand, but the log one, how is I don't didn't quite
So
understand how they calculate
So
that.
yeah, so they have, I mean, they didn't go through the method that well, but the whole idea here is that can this trajectory lead to what is the estimation and the likelihood that this trajectory, if continued further, or maybe with some more information, could have led to the right answer. It's their own model here. So like here, where, I mean, I've read this, but yeah, I just give me a minute. Yeah. So essentially, one of the versions that they end up doing is exactly this, where they uh, essentially have I'll have to. I'll get back to you on this, but
Okay.
at this point, what I remember was that hey, it's not just keyword-based matching and rogue. It's also that they're looking at a trajectory and estimating that can it reach the right answer, and that's the log likelihood.
I
Now,
see.
how they did it is something. Which is I'm not 100% sure how it happened. It says this, but yeah, I'm
Yeah. Okay. Okay. Yeah.
cool. So that's there. Then you have something, yeah. Then they do have a normalization for soft scores. One of those is if they have if it passes a threshold that they calculate, then I mean it's a simple normalization. If it's below the norm, then it's zero point 0.5 based on threshold. If it's above the norm, then you do it the same way, zero point 0.5 plus. So there is a normalization that happens, and that's probably what helps this model. Uh, but yeah, there is not a very strong reasoning as to why they did this normalization. They just said that, hey, normalization is good, let's do it. But I don't see a very good reasoning here as to why this normalization even exists, where their threshold MLP is just 0.5.
Yeah.
Cool.
I didn't understand that section very well either.
Yeah. And they're also very clear about that because their data set is biased. what they want to look at is TPR instead of a TNR or anything, because is the metric they value, because data sets are heavily imbalanced and significant number of true positive. Uh, the TPR is the one. So that's another thing here, and that's probably also introduced because in one of the experiments, the TNR was going to totally one in a base model. So I'll come to the yeah. So yeah, so basically the whole idea is that you distill the knowledge from a world model of biology into reasoning models through software verification. The same thing that they have been talking about for the last two sections. It is a good mechanism. It is probably a mechanism which can work, but just coming to the numbers first, of course. This is again a summary of what are the verifiers they had in terms of the example prompts and the questions that they are asking. One is experimental data, a couple of them is MLP-based perturbation and transcript former foundational models. Both of them come from VCM, then one comes from knowledge base. Again, it's repeating the same thing, but that we have covered.
So
So
I I don't know if you picked this up on the paper. Did you see how did they actually translate? Like you have some questions. First of all, how do you generate those questions? And then how do you translate that into something that the verifier can consume? Right?
so
I understand what goes into the verifier. I understand how to template a question for that. But did they just take like gene pairs and then like feed
yes,
them into the
they
template? So that doesn't tell me like, okay, I mean, I guess as long as you're persuaded that the LLM will be able to
So
like
they're looking at the
generalize it.
human level reasoning there. The data sets they created was something like a leave one out in both XP and MLP, and that's how they were doing it. But yeah, it's initially the whole idea is that if I take this gene and this gene interaction, if I take this gene down, what happens next?
So
That's
okay, so they just generated a bunch of questions based, they like picked random gene pairs or something
yes,
like that, generated a bunch of questions about
and
them.
yeah.
So,
So there are literally 4 5 genes that they start with. There are not that many that they start with.
oh, I
So
see.
yeah,
Wait, oh, I didn't catch that. What, like they only were looking at a few genes? I would expect you to go over thousands.
I think they're only looking at a few specific genes. I'll confirm that. So initially for training, that was there. For example, like when you're talking about prompts, right? The likely the prompts are almost the same, but yeah, it's somewhat modified based on which foundational model you are getting a reward from. Right. So that is almost the same, but yeah, they do not go through a lot of genes there. Yeah. So you have something, okay, you're here. Uh, Basically, what we call out of distribution is the out of training data set, which the model hasn't seen. It's not a generalization like it's out of domain, but it's just out of distribution. So learn to generalize on out of distribution because the problems are the same. They'll happen. So they have a NLP which they train as for a soft verification, uh, to predict the differential expression. This is what they're using as a reward as a soft verification reward model via VCM. And then you have like a one hot encoders. You have gene2 like both of them are used in different way in different ablations to be able to get different signals. Uh, so when that is there, yeah. So they compared it with experimental data on yeah uh, experimental data on uh, one cell line that is in distribution. Test and taint splits are from same cell line. So I'll come to this because this is an interesting graph and the numbers are also interesting. So essentially, it's one cell line. Initially, they start with getting gene pairs from there. Then they leave one part out and test on that one part. And then the same here, they test on that. They leave one out and then they test on it. One is basically training and testing on the same data set. Then they have four genes, they leave one out, they test on that one gene and train on the other three. The same goes with via MLP as well. So in terms of results, yeah, you have one cell line and experimental in MLP as well. Then you also have one hot, which is and gene two. These are vector styles. Essentially, so what they see is Summer is their original model. Like, yeah, Summer is a model trained on experimental data and detailed biological knowledge in the loop. Gears is a state-of-art step specialized perturbation prediction models trained solely on experimental data. And the base reasoning model is Quen 2.53b. So essentially, the numbers that they have, the data set is essentially the same. In here, this is not that perturbation data set. The TPR is what they look at mostly. It is getting to an 82. The rbio experimental one cell line works really well because it's trained on test. But other than that, Summer doesn't perform as well. Their MLP performs really well uh, with gene to work as well as one hot. Uh, then Gears and Quen 2.5, the base model isn't performing as well either. So there is a lot of jump that they see here, and especially in the true positive rate. And TNR, the one that performs best is Gears because it has a very low positive rate anyway. So
Yeah.
it's
Just to be clear, I don't think they trained on the test set. But it was in distribution, right?
it was in distribution, yeah, just to be
Yeah.
clear. So it's like they didn't leave it out completely. That's what I meant.
Yeah. Yeah.
Yeah. So essentially, it's a method of teaching how to predict perturbation based on some sophisticated models that we have already built. A real world parallel could be that you have a bunch of reports, and essentially, RLHF could be a good parallel if they had done it differently. The whole idea is that you have a bunch of text where you have to predict how what a human would predict, right? Or rather, which one a human would prefer. In this case, they're pretty much doing the same thing, but they have a lot of sophisticated models into what is going to result in a perturbation, and they're teaching generic LLM to understand that and basically be very good at that task. So a real takeaway for me here is that small models are also very good students. They can learn almost any world model from anywhere. May or may not be their own world model, but yeah, they can learn that and they get very good at a task based on just learning from a specific world model in any domain. So this is, of course, they can exhibit transfer to perturbation, which is what the results are. Then the next part is obviously that when you combine different verifiers, it improves generalization even further. So that's the next figure, not this one. Yeah, I'll just come to this figure. They essentially combined all the sources of verification and then they showed the number. It went even further. So yeah, you have experiment, then you have just the direct ones and it went even further. So coming back to that, yeah.
But if I uh disappointing that they didn't beat Summer, right? I don't think in any of those cases, or very few of them.
No,
No, sorry, in yeah, this one.
this one, yeah. I mean, yeah, Summer is almost as good, but they do beat it in the experimental all cell lines. They don't beat it otherwise.
Yeah.
And
Okay.
if
Yeah.
you're looking at TPL, not beating as much, but then the amount of compute that they use is very low compared to the original model. So it's probably getting there. We are probably gonna get to a point where we are able to maybe outperform them, or maybe at least get to the get the same kind of logic that we're getting from the specific domain models here.
Yeah.
I'm not very sure about this claim, I'll be honest, but I think verification sources keep improving performance is the essential claim that they also go to another figure and show that. But yeah, that's there. Coming back to one of the other results. So this is models trained on experimental and soft verification using VCMs, aggregate model performance, and then the metrics. So again, the same kind of results. Here, they're beating Summer comprehensively, but not in that regard. The TNR is always the one where others are winning, but in their own case, the red and the orange lines, the ones that they have trained, almost always performs really well, except for F1 score and MCC as well. But yeah, overall, they just talk about TPR as much because they're getting so many good results here as well. The other part is that, I mean, the amazing part here is obviously how much they outperform the base model because a base model is pretty dumb about these topics and they're still able to raise the performance there, which is quite fascinating for me because if it can happen in a very specialized domain like biology, it can definitely happen in a very different domain as long as you have a prediction model or a surrogate model for that domain. I mean, provided the results hold up at a higher scale, obviously. So that's yeah, that's the yeah, those are the addition of verifiers. You have the base model on TPR, you also have which is just the experimental model. Then you see how close can the other models get without using the experimental part.
This one
So
actually shows the experimental path. This was the one that I was so disappointed in, right? Like I
yeah,
feel like they didn't, this is an incomplete result because I think that with better training dynamics, like or training methodology and dynamics, they should be able to improve over the experimental data as long as you're looking like out of distribution, right? So like I think what they're saying here is that if you have in distribution experimental data, that's gold standard. And I can perfectly accept that you're not going to maybe get to that with a world model, but you can get close, and the other parts of the paper show that. But I was really disappointed to seeing that the performance goes down when you add when you add more data. And I think that there's some evidence, and I'd have to think through what it was again, but I see some evidence that they should be able to improve on that so that it at least stays as good as a gold standard, if not gets better.
makes sense. Agree. So I mean, effective addition on verifiers, they keep doing the same thing and do it. Just a minute. Yeah. So essentially, this whole chart is around that. Then a lot of this was done based on non-COT. Like they just gave a prompt, they created trajectories, they backpropagated, but there was no test time computer COT happening in this case. So they just added this line to a system prompt. A biologist will evaluate each step of the problem using logical reasoning and evidence from the prompt. Essentially, went towards a test time compute based thing, and of course, the performance jumped even further here. Like this is the I think this is the COT one. Yeah. So this is this is a system prompt. This is a conversation, and then you have to use a think and slash think. Essentially, that's the system prompt. And then it ended up with even better performance. But I think that's a generic thing where a chain of thought essentially works even better. Like you have something like a 0.88 here, 0.91 here, right? And this line essentially improved the performance further compared to the previous one. Sorry, my bad. Yeah.
Did it? Oh yeah, okay, right. So like I would have, I would have liked to have seen the the not in chain of thought and the chain of thought side by side here.
Yeah, but I mean, you have to do it up and down.
Oh, I see. No, it is there. No, no, it's not there. Yeah,
So two things here. So they do have one before it, which wasn't chain of thought,
yeah,
here.
yeah,
Then they have one with chain of thought,
yeah.
prompted.
Okay, yeah, yeah,
Then they added another line, which is that here the biologist will evaluate each step of the problem using logical reasoning and evidence from the prompt.
yeah. Yeah, yeah. No, I can see that it's better, but yeah, okay, got it. They just didn't
Slightly better, just
present it.
that, yeah.
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 Okay, got it.
And they're anyways approaching the scores of point 0.9. I mean, at that point, improving even a percentage point takes a lot of effort. So
Yeah,
probably they also needed a better data set, which they weren't outperforming at the base. But
yeah,
then you also see that, hey, like the base COT model at MCC is at
yeah.
0.03 and
It-
it's at 0.49. So there is a lot of jump that happens. Just that, I mean, their data set could have been vaster.
yeah.
So,
That begs the question though, like if it's a 3B model, how much of the improvement would you like could you just replace the experiment with, a larger model and do the same? Because presumably like whatever God model is trained on all sorts of, papers about genetics and the entire ontology database and things like that.
yeah. I think there's a lot to build upon it, both on the biology domain as well as the generic domain, because I'm trying replicating the same thing for a math domain task. And turns out DeepSeek has already done something like that before, using a surrogate model to predict whether or not the proof would hold up. But yeah, I mean, if I have the results, I'll share that. So essentially, now they're looking at answering questions completely out of distribution, like Alzheimer's and everything. And the qualitative evaluation, they haven't done this experiment in a quantitative manner, but then the qualitative evaluation is that, hey, uh, n- basically good and consistent reasoning and very few scientific inaccuracies. So they were trained for 800K steps, taking 10 days on a completion on 800 GPUs, which is not a lot of money. Like it's not even $6,000. So if you can really teach a very small and a dumb model like Quen 2.5 3B, a totally different domains world model at such a cost, then probably there is a lot more that you can uh, scale. If this scales, there's a lot more you can do. And of course, they used Hugging Face transfer reinforcement learning. So I don't know if there are other methods like reinforcement or something you can reinforce or something you can use. That's probably going to give them a bit of a boost as well because credit assignment and TRL is not as great as others. Cool. So this is the paper. They have a lot of prompts going down as well, and the ideas around this. There are a lot of work that has happened previously as well. One thing I wanted to highlight was, yeah, not this one. Sorry. Yeah, so the surrogate models have been used previously as well, and they do refer that. I wanted to highlight that part, but I'll have to search for it. Anyway, cool. So this is the paper. Uh, yeah, questions?
I mean, I've talked a lot. My my overall impression here is this is like, I mean, it is a preprint, so that's totally fine to not like. I think it obscures a lot, like with jargon and math that I think could be more clear. Um, I think that my takeaways from the paper were it's interesting technique for combining different soft verifiers. And I think that this is particularly ripe for biology because there are all these bespoke models out there. And I'm guessing that there are probably other domains in science in particular that for which it has a similar dynamic like chemistry or I don't know, or physics in which it's very expensive to do an experiment. And so that uh, maybe you can use some sort of model as a soft verifier for the reasoning process. And I think, and it's an interesting way of thinking about building a multimodal model. Um, I was disappointed because I think that's the most important thing. I was disappointed to see that they were saying that using these verifiers in distribution lowers your performance. And I think that I would like to see um, it would be good if you like I would like to see an experiment in this paper where first of all they just fix that, but also it seems to me like you should be able to use a small in distribution uh, training set plus verifiers to create a sort of a model that performs um, as well as the experimental data in distribution and better than it out of distribution.
Uh, Yeah, I do think that that's the case, but I also think that they set out on a very narrow problem statement. It should generalize, but this is also like the first step in that experiment, whether they can really codify world models into an LLM. And that's why the data set was narrow, the problem statement was narrow, and the model was small.
Yeah,
The technique, and if it works, probably it's a good thing simply because right now where we are at with reward models, we are kind of assuming static priors. The kind of surrogate models work better in terms of a reward model simply because you can keep capturing the changing priors that people have. It could be as simple as, hey, what is the probability that this business plan succeeds? Given based on thousand, of course, a random example, but given thousands of examples previously, you can pretty much use that as a predictive model for something. And we have used predictive analytics in the past, just not for an LLM. Probably those are the domains where this can work as well. Just
yeah.
that you need access to that kind of data to be able to build out the predictive model first to that knowledge sources, build out that soft verifier first, and then go for something like this.
Yeah. Yeah. So I agree. So like as a stepping stone towards a model that you're able to converse with it generally about biology data and have it reason through complex questions. I think it's a good stepping stone in that direction. I agree.
I'm so I came in very, very late. Came in around 5 minutes ago. I just maybe my question might be um good for anybody else who might have come in a little late, but I guess from what I'm gathering here, the model that you guys that the paper authors trained was one that was given the domain of like biological, a certain specific domain of biological knowledge that was contextualized by biological models. And there was kind of a surprise by the model's ability to generalize at the extent it did toward those mathematical models that kind of contextualize that domain space and its ability to kind of respond and interact with that environment along with kind of some reinforcement learning. Is that kind of a solid approximation?
Yeah, I mean, that's pretty much the you have a base model which is not trained on anything in biology, and it is able to compete with very specific, task-specific models in bio that were made through a lot of experimentation and collection of a lot of data.
Right.
So, yeah, and that's what you're getting at, and especially a very small model that is able to compete with probably the bigger models that are foundational models, but not LLMs in that regard.
So, for an interesting thing for me is that this paper shows kind of extends outside of the domain of biology, but kind of the domain of any scientific theory that can be parameterized by models that describe the fields of the space that said um, machine learning model would be attempting to generalize toward. I'd be interested. Are all of, are is there kind of were all of the biological models that contextualize the space differential equations, or were they? I guess were they all kind of in a similar mathematical form, or did they extend out to different mathematical forms?
I think by mathematical forms, you're looking at MLPs.
Differential equate. I'm talking about the biological models
Oh,
that contextualize the space that the machine learning model was generalizing. So, like, yeah, I assume most biological models are differential equations, right?
I'm
Uh,
not very sure about that.
Okay.
no, I think some are for sure, but I think it looked to me like the ones that they were using were different types of neural networks. So from simple multi-layer perceptrons to transformer-based models. So
Well,
the verifiers themselves
uh-huh.
were also neural networks. I
Okay.
think
Okay.
yeah,
Mhm.
and I think like if you think about the mathematical models of these things, there are definitely differential equation based ones, but some of them are not, right? Like,
Okay.
yeah.
So just to answer a question by Peter, uh, I came across this paper because I was looking for different verification techniques. I was writing a blog post about it and searched on O3 and it surfaced this as a interesting thing. And I think that was somewhere around August when the paper had just come out. I read through it and I understood that, hey, if this generalizes and the techniques go well, this can be far more reaching than just this domain. So I thought, let's pick it up. And it took me 2 months to pick it up.
Wait. What? Tell me more about this blog post on verification. How?
Uh,
Yeah, what's going on there?
So essentially, it's a blog post around environments, but the key in environment is how do you verify the task has been done. So the whole idea here is that at some point, everyone is assuming that the priors would stay the same. And that's where you can have a very static reward function that can just work. But that's not going to be the case because a lot of for humans as well, priors change. The evolution, I'll send you the link as well. It's a long as blog post. I already put it. But yeah, in short, the idea here is that if you assume that RL is basically generalizing the priors instead of, hill climbing on an iterative manner, uh, say it is generalizing the priors, then the model needs to have priors. The priors can be coached through one, generating enough training data, but this is the second idea where it can be coached through just giving a very specific domain reward model or a surrogate reward model, as they are called. In certain cases where that is not going to be enough, for example, when you are buying on Amazon or someone else is buying on Amazon, that's very personalized and preference model scenario where I don't know how to train it today. But then that's the third kind of reward model that these LLMs would need because you can't have a very generic static prior that, hey, can an LLM buy, say, a jacket on Amazon? You want something which takes into account preferences for different people and it cannot just be verbalized preferences. You need a sort of a recommendation system there. And that's the kind of trajectory we are moving towards, just that we are not there yet. And I don't know what it looks like. Just that the middle part here is the surrogate aspect, where you model a real world thing into a prediction model. And then you end up in a place where you are able to at least codify most of it into an LLM that can generalize.
Yeah, it's very comprehensive. Actually, yeah, I'm looking forward to this post.
Yeah.
We tried. Yeah, I'm pro more recommendation systems. Um, in our pipelines in general. Your comment made me realize actually that these systems are a lot closer than I thought. Um, yeah, I usually put them in a different mental bucket, but maybe I should not.
Yeah, but the architecture point that needs to be solved is how do you have different reward models for different preferences? So in the same model. And that's probably something
Yeah,
DeepMind has a solution for with their reward heads, but nothing much has come out. I've seen a couple of papers around it. That's probably one way of doing it, but yeah, don't know. And these labs are not really publishing those kind of things anymore. I mean, for everyone who knows Anthropic would have discovered it a year ago as well. No one has published anything, so we don't know unless we know the people who have done it.
there's some comments in the chat.
I think they went on a discussion. I'm just confused as to what that discussion is about. Yeah.
Yeah, see, maybe CJ, you want to jump in?
Oh, I was just responding to what I understood
Oh,
somebody to be
okay.
saying.
Got
Not
it.
directly. Yeah, yeah. But kind of just reaffirming how you guys explained to me that the models that we're verifying, the model that's being tested, are neural networks. I was contrasting that with how the laws of a system might be expressed through differential equations, which is hence why I assumed it was differential equations that were contextualizing the system. But I understand what you guys mean, that no, these other neural networks, these other transformers are acting as direct verification to the model being tested, this transformer.
Yeah.
Correct?
Yeah.
Yeah.
Mhm. Yeah.
Mm. Awesome. Well, I think that we are out of time. I think, Sean, we have a paper for next week already, right? I thought,
Dude, as you can clearly tell, I have trouble keeping track.
yeah, I do too.
Source of Truth is in Discord. We'll coordinate in Discord. But Ankit, I'm very impressed by this coverage. I'm really looking forward to hearing more from you. This is the spirit of the paper club. It's like discussing stuff like this.
Yeah,
Thank
thanks a
you.
lot, man. I'm really, really glad you picked this paper.
And it's different. I hope that it generalizes because then we'll have something we can build startups on. Because
Yeah.
Yeah,
essentially, yeah, let's
it
see.
will generalize if the theory works. And people have been trying to put this into, but so far we haven't needed much good stuff in the world model space. But like Meta also did this like code version
Yeah.
of yeah. Maybe it'll work this time. I don't know.
Let's see. Yeah.
Awesome.
Yeah.
All right. Thank you
Okay.
guys.
Thank you.
Later, guys.
Bye bye. Thank you.
Oh.